Okay. So let's quickly review the naive Bayes classifier that we had last Monday. Basically, what we want to calculate is the posterior probability of like a certain class given a certain input, but that is often not very easy to do. So that's why we try to flip the task around through the, using Bayes rule and express the posterior probability as the prior times the likelihood divided by the evidence. And we learned that prior is basically just the like probability that a certain class is present or not. So that's based off of our data set. So most of the time we would hope that this is like an even split. So you have like 50% of your observations are for class 1 and 50% of the observations are for class 2. So you would just put in like 0.5 there. The evidence is basically the likelihood of observing a certain pattern or certain like input. That is basically the margin over all classes to observe this pattern. And then we have the likelihood. That's the interesting part where we basically compute the likelihood of a certain observation given a certain class, and we can calculate that from our data set, so that's a lot easier than the posterior. We had an example where I think this is a new one, so we were like this new message is like free pharmacy, and the message, this is our X that we observe, and we made an additional, basically we have to calculate this here, but we made an additional assumption where in our message each word is independent from each other. So they could be pharmacy free, that would be the same outcome, okay? But obviously that is not often, or like not really the case in human language, so there's dependencies between consecutive words. But anyways, like in the naive Bayes approach, we don't consider that. And basically, we compute the prior based off of the labels that we observe. So we have 8 in total, and we have 3 spam and 5 non-spam, so we can get the prior very easily. We then also can compute the likelihoods, which are basically for each word we would have to see like how often does free happen to be present in spam messages. Well, we have it once out of, let's say, 9 words, so it's a 9th, and pharmacy is much more. Out of 9 words we have it 3 times, so that's 3/9. So we can easily compute these variables. And then the bottom part, the evidence, we only need that in order to make an assessment of basically knowing or like getting the actual posterior likelihood. If we just want to like classify yes or no, we don't really need to compute that bottom part because it's the same for both like classes where you have like spam and not spam, that basically like can be simplified out. We just talked about that. So the messages basically each word is independent from each other, so we can write this probability as a product, and we can often make this assumption. Even though it's most of the time it's probably not exactly true, but like often this just makes the computation and the assessment much easier. All right. So we had the prior is 3/8, or 5/8. Then we have pharmacy given spam. That was 1/3. Pharmacy given not spam. We have it once out of 3 times 5, 15, so 1/15. And then we can put that in down here, basically, and then also down there. And in the end, we can basically out that this spam message, or this message is 0.625 spam, and very easily we can assess, oh yeah, if we just subtract 1 from, like 1 minus this likelihood, we know that this message is likely spam. Okay, so this is kind of like just a brief walkthrough again, how the naive basic classifier basically works. Any questions to that? Okay. We're possibly going to do homework on that. All right, so let's continue with the new lecture, and I'm just also going to, we talked about the decision trees again, we walked through those. So basically what we need to do is we need to find out which splits are optimal, and we had this example here where we found out that, okay, if we take outlook as a split, we get 3 subsets. This is the optimal split here, and then from each of those, if you would see here what the outcomes would be, you would see that I think the next step will be based off of humidity, where high humidity the player doesn't want to play, but normally he wants to play, and for the other one it's wind, and you can create these perfect splits at the bottom. So basically you walk through at the top, you walk through this tree and use this to identify how like you would decide if the person is going to play tennis or not. So we talked about the fact that we need to try to improve the entropy at each of these splits, and it's based off of this divide and conquer scheme. So like first we have the entropy of our entire data set, and then we make decisions and we want to know what the subsets here, what their entropies are, and we want to have the split where the entropy is optimal. And what we need for that is basically these splits shouldn't be too tiny, like it shouldn't be just one item in each of those subsets, because then obviously they are homogeneous, they don't have entropy anymore, but their weight is small. So at the end we don't want to have like too wide of a tree or too narrow of a tree. And computing entropy or these kind of other homogeneity indexes is important in this case. So we had talked about entropy Gini index, maximum likelihood for, or like maximum class likelihood for each of the nodes, and I know it's a bit hard to like implement from scratch, but basically I would like you to understand that at each node you have to make a recursive decision where basically you identify a decision that splits this set here into optimal 2 subsets, and to find the optimal 2 subsets you have to compare the entropy that you have at this point with the 2 entropies that you have at this point. And to be able to compare those together, you basically have to weigh how much weight each of those subnodes has. So like if they are large, they have a lot of weight, okay? And if they're super tiny, they don't have a lot of weight. And you kind of like want to create some sort of average, but a weighted average. So if this is larger than this one has more weight than that one, okay? And you compute the entropies in each of those and compare that with that one. And the one split based off of a decision here that basically reduces the prior or the previous entropy maximally, that's the one you're going to choose, okay? So you have to just try out all the splits and see which one gives me the best new entropy, and then that's the one you're gonna try. And again, through recursion, this decision becomes smaller and smaller and more less and less difficult, because you have to look at less and less data points. Okay.
Can you give us an example? How do you get the number 9 over there?
The what?
The number 9 over
there. Yeah, it's a bit unfortunate, but so if you if you look at this data point here, right? So you have 15 days, 14 days, and then basically at the start you count how many yeses you have. 3, 3, 3. So it's 9 yes. So that's why you have at the start of everything, I have 14 days that I have as data points, and 9 of them he played, and 5 of them he didn't play.
Okay.
So that's basically, that's how you start off at the very beginning. And then like using these two numbers, 9 and 5, you can calculate your initial homogeneity or entropy, right? So you would see, okay, like it's not great. There is a weight towards one class already, but it's not perfect. It's not a perfect split, right? You don't have just one class. So now you want to split, and you want to split so that this homogeneity gets better and better. Okay, and at the end, what you would want to have is exactly what we have here, where there's always only one class in there, right? So you have always a 0, and here you already have just a 0. Or like just yeses, I think. Okay? Alright. And yeah, so that's basically what we make as a decision. And then, so we have now the labels, no, yes, yes, no. And so the outlook here, like, so we get this new data point, we want to know what we're deciding. Based off of the inputs, so you check, okay, outlook, which subset of the tree do I go down? Well, I go down this way, and then I look at wind, which is weak versus strong, and then we say, yes, he's going to play. Okay? Alright, so this should be fairly simple. We also talked about how regression trees can work, where basically instead of increasing the homogeneity of these points, or like these sub groups of observations that fall into this category, so we're not optimizing like entropy in this case, but we're optimizing variance from a mean value that they have. Okay, so what you want to have is a lot of values in here that are like located very closely around one mean value. Okay, so if they are so if you have like, let's say 10 values in there, maybe we can draw this real quick. Wasn't there a button for video? So basically, if you decide, so you have a function, and if you decide that all these values fall into the same subnode, then you would probably say, okay, like this is my mean value around here, but then you also have to compute like basically the variance of this value, and if you decide that this variance is too much, well, you would split again. You would split probably somewhere here and somewhere here, and now you don't have one tree anymore, but you have like kind of 2 leaves. So this one's much closer, and then these guys are falling into that category, or like might be on the top. But you want to try to like have more similar, or like instead of like improving the entropy of the items in the leaf node, you try to reduce the variance of them, like just the value variance they have. All right, and then again, you can play this game however like detailed you want to play it. The worst case, again, you would have a very wide tree where every single item basically, or every single leaf node only has one value in there, and the one value is used to calculate the mean and the variance, and both of them are going to be so the mean value is going to be the value, the variance is going to be 0, right? Because there's nothing to calculate the variance over. Okay, so that would be perfect trees in a sense, but also very bad trees in the sense of in the sense that you want to make sure that you can derive some meaningful rules or derive some tree that's not completely overfitting on your training data. Okay. All right, and then we discussed that you can also start pruning sets where, for example, you would decide like if this split actually gives me a benefit or not, and what you would do is you calculate the performance of this, of having this split and not having this split. And then if the performances are equal, you would like prune off that subpart of the tree and would create a node there and then just stop. And you can only do that with additionally held out data, right? That makes sense because if you would do that on like the training data itself, or on the test data itself, you would obviously violate some experimental rules. Okay, so pruning and validation of these trees should also be done with a validation set that is held out from training and is not part of the testing phase. Okay, and I think there are functions in scikit-learn, for example, where you can do pruning on trees. Okay, and so why do we want to prune? Does anybody?
Oh. We had a power surge.
Power outage.
Make sure your computer is open.
Sometimes I feel like.
Oh wow, we really got it. That was a transformer.
This one's a more.
That was a transformer. That was a transformer. So the transformer
well,
went.
So let's talk in the dark.
Okay.
I still have my screen here. So why is it good to? I should not have that plugged in right now. I think.
Yeah,
Because it started to do weird things, and the computer lives without batteries, or without electricity on a battery. So
Yeah.
leave it like this. So why do we want to prune trees? Overfitting and like why? Do you remember a rule that we talked about where we said that a simple solution is often to be chosen over a not simple or like a more complex solution? Occam's razor, exactly. So we in general we want to choose the simpler solution over a more complex solution because it has a higher likelihood of generalizing well on new data. Okay. And then we talked about basically if we have a tree, how we can basically extract decision rules. Like for example, you're tasked with coming up with a machine learning approach to a problem, and you're basically telling the stakeholders, here, this is what I found. This is the result. And it's a black box and nobody knows really what happens, right? And then they might ask, okay, like, how does this work? And like, okay, we can come up with a decision tree and then basically derive decision rules based off of this. And what basically happens is that you can now split this tree into a number of rules, and the rules are the same number as the number of leaf nodes, and you can just walk through the tree and make these decisions and concatenate each decision that is connected. So decision node to decision node, you just concatenate them with ands, And decision nodes to leave nodes, well, you just make a decision after that. Okay? So you can say then y or then like the other side. So you can say so basically it's just if statements. And one of the interesting things is like we built a system like that, and I like basically calculated the decision trees in MATLAB or scikit-learn or whatever you want, but then we had a production system which didn't have access to MATLAB. It was like an interaction, like where you have a virtual human talk to a real human, and we didn't want to have MATLAB run in the background and do the machine learning. So what we did is basically learn decision trees, write out these rules in XML format, and then you have the interaction or the virtual human just load the XML file and do these rules. So you can split down these trees into very simple if statements that you can also update during runtime. You don't have to compile this. Okay. And then if you have multiple leaves that have the same label, so if there's, for example, another 0.8 here, you can combine paths, so this path and that path through ORs, so that's easy too. Okay? Any questions to that? Alright, and then we had briefly discussed that we can also come up with more complex solutions or multivariate trees where basically you're not allowed to just use one dimension of your input vector in the decision, but you're allowed to use two of them or multiple, like whichever many you want. And in this case, for example, we learn a linear separation that goes through a two-dimensional space. It's basically a line where this value here basically gives us an idea like how far away from the origin we're moving, and these other two, they just tell you like what the orientation is. Okay, so that's how you can interpret that more easily, and like you can see that this is the same example as we had before with univariate trees where we needed like 2 or 3 decisions, and here we just need 1 decision. So these are obviously more powerful. And you can imagine that, and I mentioned this earlier or last week, where you have trees that are consisting of much more complex rules than these like simple binary decisions. It could be like neural networks, it could be something else in there. Okay? So I hope that makes sense. So you like decision trees are not reduced to just having binary decisions. They could be very complex and could be used in very, very large tasks. Okay, I'd like to give you a little example where we used decision trees in our work. And before I do that, I'd like to show you a little motivational video. Basically, so the project Cicero that we are working on is a project to improve like presentation skills of individuals. And the motivational video, I'm not sure, maybe I've shown it before, but basically this individual is competing in the World Championship of Public Speaking.
He wrote his life story down in a journal with a twist. It was a poem, one long poem from start to finish. And this from a man who never went to school.
So basically, he uses gestures, different voice, he changes the posture on the stage. And basically what we want to do is we want to integrate all this information and assess how good a person is in public speaking. Another thing is also like you cannot look at the modalities like voice and gestures in isolation, because also they work together, right? Like if I emphasize in the voice, I should also like display an emphasis in my gestures. And obviously, like this guy doesn't get born with these skills, and he basically had to learn them.
This story is about passion, obsession, and blood.
And basically, you can see how he trains, and I believe that most of you probably have exercised public speaking at home as well, and like maybe in front of the mirror, maybe in front of, like he did, pillows, where you have tortured family members or friends, like I have. And so we at ICT, we basically said, okay, let's try something new, and we proposed to use a virtual audience to give you feedback. And there are three main components to this. As I said, we need to track the behavior of the individual, and we get at eye gaze, facial expressions, gestures, and so on. And then we basically assess, using decision trees, how the performance of the person is, and like the decision trees is one approach. Like we have multiple ones, but the production system, it's very easy to build that with decision trees. And so we basically assess how good they are on 10 categories, like overall the flow of speech, the gesture usage, and the intonation and stuff like that. And then we want to provide them feedback. So the virtual audience gets to know how well they're doing, and then they can give feedback like falling asleep, or they like can nod and smile interestedly and stuff like that. So basically this is how we're assessing the performance, and we have some strategies to provide feedback to the user, and it works quite well actually. So we have a bunch of studies on this, so people can use virtual audiences to learn to give presentations. All right, but it's not as simple as I mentioned before, where you have one tree and you make an assessment. We actually use many trees. So we have, I think in total, like 20 or 30 very simple trees, and they're all stored in like XML files. And what these trees do, they make a few simple decisions, right? Like they go left, right, with just 2 or 3 questions. And what they produce is a continuous output. So each of those trees is a regression tree. They're not decision trees. They're like not classifying. They're like not saying good or bad speaker. They say 0.5 speaker, 0.7 speaker, 0.3 speaker, okay? And then what you do basically to combine all of these experts or ensemble of this entire ensemble's decision, you basically learn a weighted sum between those. And I think in this one, it's just the average of the 3 numbers. Yeah.
Oh, why do you have 20?
It's a validation parameter, so you would try out with 10, 15, 5, and
then
you
20
find out.
just work.
Yeah. And again, validation with the left out data set. Yeah. And so you would learn like a weighted sum between those. And in the simplest way, you weigh each output similarly, but you might trust one or the other tree more than another one, and so on. Okay. All right. And so what we found is actually that we can learn what experts assess, what experts think is going on quite well. And in this case, our metric is not a distance metric from like the actual value that experts assign to these certain speakers, but in this case, it's basically a correlation between what we think is happening, or if this is a good or a bad speaker, and this can be visualized a little bit better if we show a regression through the data points that we have. And in this case, it's not performance, but it's anxiety. We can evaluate basically how well or how much anxiety certain individuals exhibit. And we found that we can predict the anxiety of a speaker quite well. And this is also done using these sample trees. All right. Yeah, and we assess the anxiety through the PRCS, like the what is this, public speaking, fear of public speaking score or something like that. Yeah, so you can give that to individuals and they just fill in the questionnaire, and based off the questionnaire output, you assess how much anxiety they have in public speaking. Any questions for that? Okay, cool. So this is just an example of how you can use trees to calculate like an output or predict certain performances. All right, so now we can basically start a new topic, which is linear discrimination, and it's kind of like a little bit of a shift from what we have done previously, where we have always, or like for example, naive Bayes, we have tried to calculate this posterior probability, and we had this likelihood-based classification. So it's like this is more likely than this class, or this class is more likely than that class, and that's why we make this decision. Okay, so we have to calculate all these points here. There is, however, a different class of classification that we can discuss, and this is actually a lot more popular these days because most of the neural networks are discriminant-based classifiers. They don't necessarily compute a likelihood or a probability, even though you can learn them to do that. But what most of them do, they basically give you a value that tells you if you should choose one class over the other, and it is computed through a discriminant function. For example, this GI of x given certain parameters phi or whatever, and we're gonna learn. So the discriminant function is always going to stay the same. Like we're deciding if we want a linear function or if we want a quadratic function or a logistic function, but these parameters are going to change. Okay, so we want to find the optimal parameters for a certain discriminant function. In decision trees, the discriminant could change all the time, right? Like you make different decisions all the time, and at the end you have a different decision rule for each different tree. But in this case, the discriminant stays the same, but we want to find the optimal parameters, okay? That's what we're trying to do. And this is the same for linear discrimination, logistic discrimination, and also neural network, and so on. Okay, so the same functions or the same process is applicable to all of them. And we're going to talk about linear discrimination first, and then we're going to talk about neural networks in the second half. I'm not sure if we're going to get to that today, but the next time we're going to have a lecture, we're going to talk about neural networks and how we learn in neural networks. But it's basically the same process. So yeah, what we need to do, or we need to remember, is that the decision or discriminant is dependent on a set of parameters, and these parameters are what we need to find. Okay, and that is, so we need to learn the parameter set that optimizes the classification accuracy given the training set. Obvious, right? Like that's again, we need to learn that. We have the same training set as before, and we need to identify how these parameters work. We don't care about estimating class densities. We just want to find like a line to separate the class, okay? Or like a curve or a region that separates out our classes, okay? No more density estimation, like in naive Bayes, for example. So in this case, we're looking at the linear case where we have two types of parameters that we need to learn. first we need to learn weights that basically give us an idea of like how important a certain input dimension is. So we have an input vector that's x, and each of those weights, wi, give us an idea of like how important each dimension of this vector is. There might be a couple of zeros in there. That means if we learn that some of these weights should be 0, that means that this dimension has nothing to do with the target that we want to estimate. Okay. If it's positive, it means there's a positive relationship between that input dimension and the output. And if it's negative, we know it's a negative or like an inverse relationship between that input dimension and what we want to do. And the W0 here, that again just gives us an idea of like how far away from the origin we should move this line. Okay? So this is learning a line, learning a linear separation between classes. And we're gonna talk about like how you make a decision based off of this in a second, but basically the problem formulation is that we want to find the parameter set W that minimizes the error. And because most of the time there is not like an analytic solution to the problem, we need to do something else, and this is called like there's something else that we're going to have to do are these gradient methods, and I would like to introduce those gradient methods today, both mathematically as well as like visually, and we can talk about problems of those the next time with neural networks, because neural networks always run into trouble with the gradient methods. And so what we're going to have to talk about today is like how these gradient methods like work and in simple examples, how they like geometrically or visually look like, and then we also need to identify what I mean with criterion function or loss function or cost function, etc. So these are or error that we want to minimize. So we need to identify what these all mean. Okay. So, but let's start with this example first. And I kind of talked about this already, where basically in this simple model we basically compute the output or discrimination as a weighted sum, which you have here. So these are the weights, these are the inputs. This basically is the sum, and then you add this W0 bias parameter. But what they are basically is just a scalar product or a dot product of the two vectors, of the weight vector and the input vector. Okay, this is we'll get back to this when we talk about perceptrons and stuff. Okay, and here's an example again for the inhibiting versus enforcing kind of relationship, where in credit score, for example, yearly income is a positive impact, so the weight is greater 0 on the credit score, while the debt is a negative impact on that, and it has a negative value. Okay, so that should be clear. And geometrically, this can be interpreted as such, where if we separate two classes, we only need to learn one discriminant, and this is kind of like giving you an idea how you can combine two discriminants into a single discriminant, basically, where you just define, okay, we have one discriminant here and the other here, and two different sets of weights, but in the end, it's just a difference between the two sets of weights, which basically comes down to a unified set of weights. Okay, this is through simple reformulation a proof that you don't need to learn two discriminants; you just learn one. Okay, and what you now do, you try to find through gradient descent or gradient methods. You've tried to find this line here that splits up our space perfectly into squares and crosses, and geometrically defined everything that is on the right side of this line is going to have a positive sign, like a plus, and everything that's on the left side is going to have a minus. Okay, that's just you can calculate that through through geometry basically, or like vector multiplications. And everything that is on the line is going to be 0, right? So so this is what this basically learns. And so if you want to make a decision, class 1 versus class 2, you calculate this G, and you choose, if it's greater than 0, you say it's class 1, and if it's less or equal than 0, then you choose class 2, or if it's, if it's actually equal to 0, you are out of luck. You basically have to decide with the coin toss which one it is. Is that clear? Okay. So the hyperplane divides the space into 2 half spaces, yeah, X is on the decision, so we talked about this, and we talked about that as well. All right? So what if we have more than 2 classes as a problem? So we have k many different classes. In this case, you would actually have to learn k discriminant functions, and you would have one for each class, and you decide if it's greater than 0 for the ith one. Well, then you say it's class 1 or class I, and you would discard it for the others. So it has to land on one side of the positive sides if you have multiple classes. You'll see an example in a second. And what ideally would happen is that for every input, only one of these these GI discriminant functions would be greater than 0, and all the others would be less or equal than 0, right? So that would be ideal. That means that each point is only on the positive side for one single discriminant function. But that often is not the case, and we'll see what happens then. Basically, if it's not the case, you can use the maximum. And so what does that geometrically mean if we choose the maximum of these values? So if we just use the one, so let's say you have points or data points that fall on more than one positive side of these discriminant functions, okay? So you don't know which of these classes it belongs to. It could belong to both of those classes. And you decide to take the maximum. What does that mean geometrically?
It's like farther away from the line.
Exactly. So from which line is it further away? And you'll see basically, again, also in this case, right, if this is my discriminant function and I'm right here, I'm very close to the discriminant function, so I'm very uncertain if this point is actually class 1 or class 2, right? But if I'm out there, I know very well that I'm not class 2, okay? So that's kind of the geometric interpretation here, why choosing the maximum is good, okay? And this kind of looks like this then, where basically you have 3 of these discriminants, and each of them basically have, so this one leans over that way, so that's why the positive is here. And so for H3, you have all the points here are negative, only these points are positive, and yeah. But some points might have multiple positive values. And does anybody know where to locate those? So one of them we could say, for example, is here, right? And so this would be a value that has a positive here and a positive from this one. So which class would I choose? Would I choose that or that class? If it's here. C3? Yes. Why?
Close.
It's closer to these guys, but it's also further from that one, right? So basically this Voronoi tessellation here, these lines give you the decision. Like when I'm here, I don't know. Both of them are equidistant, right? But if I'm here, I go that way because it's this line here discriminates between this and the rest, while this line discriminates between this and the rest, right? So when I land here, I go this class, and I land on this side of the line, I go this class. Okay? All right. So this, however, still requires us to have like the ability to linearly separate our spaces. Sometimes you might have a problem where like this class goes all the way around here, and then you like have trouble to split out that class properly. Well, the way to do that then is you are learning a pairwise separation where you basically, for example, in this case, like to learn this class, this separation between class 2 and 1. So H1, 2 is between those two. You ignore all the data points down here, okay? Because otherwise you would have these points fall on that side again, okay? So you have to make multiple decisions, and I think, yeah, k times k minus 1/2 many discriminants you need to learn, and if you have a hard decision that's available, like where you only have one positive and all the others are going to be negative, you can make these decisions based off of this rule, but otherwise you just apply again the maximum rule, okay? So this is kind of like geometrically how this works, okay? And let's take a brief 10-minute break, and then we'll talk about gradient descent methods, okay? All right, so let's get back here at 11.